The last lesson in this module will cover the dark side of bioreactors. Just kidding, but we will discuss possible chances for pollution swapping to occur with bioreactors, which we really just want to avoid. We've talked about most of these issues in earlier videos, but I also wanted to have them summed up here all in one place, starting with woodchip bioreactors will always have a startup flush of organics. This flush includes things like carbon, phosphorus, nitrogen, phenols, tannins, things that are found in wood. These flushes can also happen after the wood chips have been dried out, but most generally the first flush of these compounds will be the highest. Here you see tannic acid concentrations in bioreactor outflows from the time that the bioreactor was built. Generally, these compounds decrease over time. These compounds flushing out decrease over time, but you see the spike here at the Dudley Smith Farm bioreactor after that bioreactor had been dry for a summer period. It's important to consider this if you have a situation where you're outletting a bioreactor to a sensitive water body, but also consider this carbon coming from the wood chips fuels the denitrification process. This is how bioreactors work after all. Regarding the phosphorus leaching from wood chips, all wood chips contain phosphorus, although these phosphorus concentrations in the wood are orders of magnitude lower than the carbon and the nitrogen concentrations in the wood. However, the phosphorus concentrations that can leach out of the wood chips can be relatively high, like in this batch leaching test that we did. Keep in mind, environmentally relevant dissolved phosphorus concentrations to avoid eutrophication can be as low as 0.07 or 0.03 even milligrams dissolved phosphorus per liter. Pretty low concentrations. Phosphorus leaching from wood chips primarily appears to be a startup issue, like you see in this study here comparing year 1 versus year 2 of bioreactor operation. Year 2 even shows some DRP removal here. This indicates to me that there are still some things we don't know about wood chips and phosphorus. Moving on to greenhouse gases. One of the most common points raised, frankly, by people who could be opposed to bioreactors is that we're producing nitrous oxide. Nitrous oxide is a natural step in the process of denitrification. But far and away, many studies have shown nitrous oxide emissions from bioreactors are small. For example, many studies have shown that on average, less than 1% of the nitrate removed ends up being emitted as nitrous oxide. Why? Because bioreactors are specifically designed and operated to do denitrification efficiently. So we know that most of the nitrate that's being removed ends up as stable dinitrogen gas. Yes, some nitrous oxide is produced, but it's a very small percentage. Denitrification is influenced by factors like DO and temperature, so these same factors influence nitrous oxide production. For example, relatively more nitrous oxide can be produced under very short retention times in bioreactors, but in general, bioreactors are not pollution swapping nitrate for nitrous oxide, and the literature is pretty consistent on that. I'll also mention methane, which is another greenhouse gas. You know that from our redox potentials, methanogenesis happens under very reduced conditions. Bioreactor methane emissions are more likely to be exacerbated with warm water and long HRTs, but just like I believe we can manage bioreactors to minimize nitrous oxide production, I believe we can also manage them to minimize methane production. For the sake of full disclosure, with the recent emphasis on climate-smart agriculture, I do think there is more to learn about gas emissions at bioreactors. In addition to methane production, another reason to avoid very long bioreactor retention times is that we want to avoid sulfate reduction. The reduction of sulfate naturally present in drainage water results in hydrogen sulfide, H2S, which is 1, kind of stinky like rotten eggs, so it's not a very pleasant gas. 2, it can be a noxious gas, which can be a concern for confined spaces. We don't really have confined spaces at bioreactors, but probably most importantly is number 3, sulfate reduction can be linked with mercury methylation. Methylated mercury is a form of mercury that can bioaccumulate, so it's definitely something we want to avoid. Bioreactors serving as a source of methylated mercury has been documented under sulfate-reducing conditions, but consider, mercury methylation is a natural process that also happens in wetlands, and this process can be managed. For example, maintaining at least 0.5 milligrams nitrate nitrogen in the bioreactor outflow can suppress this process. This is one of the biggest reasons we use drawdown plates in the outlets of bioreactors, so that the bioreactor can always be drained within 48 hours and you don't have stagnant water. Lastly, we've recently seen some bioreactors slumping or subsiding sooner than expected within the first couple years of being built. We're still trying to figure out if this is due to the wood chips not being great or differences in flow conditions like wetting up and drying out. But one of the concerns here is that it could be a safety hazard if the sidewalls collapse. Subsidence is to be expected over time, but it is one of the next big things that we're studying. Thanks for joining. See you in the field.